All right, good morning and welcome to E141. Let's get started for today. So what we're going to do today is continue with introduction to wires and expand our discussion from last time onto transmission lines and inductive effects. What happens when you operate at ultra high frequencies, when you need to worry about inductance as well, and then we'll try to understand how to include that into our analysis. So we'll then devise electrical models for analysis of this behavior and do a couple of examples. Announcements for this week: no labs, no homework. Lab 5 will go on next week. You're almost done with the labs. There is Lab 5 and Lab 6, and then after that you'll have one more hardware lab. We'll do a little bit of probing in the lab and get a feeling of how does that look like. Today, this evening is a review session for midterm. That's from 6:30 till 8:30, 2-hour review session that will be in 277 Corey. And as I said last time, this will be your chance to ask any questions you like about lecture material. If you want me to walk through some particular example that you had difficulty solving from previous midterms, from homeworks, from examples from the lectures, anything, that will be your chance to clear out any difficulties that you have, and then you'll have another full day to study for to digest that for before the midterm. The midterm will be on Thursday, and there will be no lecture next Thursday. So the midterm will be in the evening, 6:30, in the same room, 277 Corey. And the material, you should know this by now, there'll be chapters 1, 2, 3, and 5. So it's basically everything that we covered up and including the scaling. So that's lecture 9. So the wire models will not be covered on the midterm. Okay. The review session will be divided between myself and the TAs. I will be there for the first 1 hour, and then the TAs will help you out for another hour. So what we intend to do is basically just take any questions about the material, eventually walk through some of the problems, and I think TAs will continue to walk you through the Spring 2003 solutions, unless you have some other demands and you would prefer to go over some other problems. A review session will not be webcasted. We don't have the webcast technology in that room. All right. So last time we gave introduction to wires and analyzed wire capacitance and resistance, and then we went into electrical models that capture the impact of these parasitic elements, and then we analyzed various models for the delay calculation purposes. And what we are going to do today is wrap that up and continue into the same topic by introducing inductances and then see what kind of models are appropriate for that analysis. So last time we first introduced interconnect capacitance, and this is basically the problem that we are trying to analyze. It's a lot of interconnect, a lot of wires going at different levels across each other, and now the question is, how do we really understand what's going on in this pretty complex structure on top of our transistors? So we first started with the capacitance, and then we began with obvious parallel plate model, when we have basically a sheet of metal running over dielectric, and where there is some current flowing through that piece of metal that is W wide, L long, and H tall, then it forms a capacitive plate with the substrate. And there is electrical field lines going vertically from the wire down to the substrate, terminating into ground. And then we said that the overlap between this metal line and the substrate forms a capacitance, two plates of a capacitor. And then the capacitance of that capacitor is equal to basically the standard formula that we are familiar with from the transistor analysis. It's basically epsilon of this dielectric divided by the thickness of that dielectric, and it's proportional to the overlap area. So it's inversely proportional to the distance and directly proportional to the area of the wire. And then we went into a scaling a little bit and discussed several scenarios where you have long wires, short wires, and so on, and then you can basically derive expressions for various scenarios for wire scaling. And we said, well, this is a really simple model that is not really applicable to practice, but it's good to start from. So there is other components that we need to worry about, especially that we know that the scaling of wires has adopted a trend that not all the vertical and horizontal dimensions scale by the same factor, but rather the height of the wire stays about the same. And then you basically just made the wires thinner and thinner as we scale technologies. And then in that case, we no longer have this really parallel plate thick wire assumption. And it's more like this really converges to this case where you have more of a round a piece of metal going on top of dielectric, and then we have to start worrying about this fringing capacitance. So parallel plate was dominant long time ago, and then with technology scaling, this fringing capacitance became really the dominant component. And then you can simply analyze the impact of both by decomposing your wire into two equivalent capacitances, one of fringing capacitance of a round metal line and another of rectangular line that you get only parallel plate capacitance from. So then we gave a little bit of insight into relative contribution of these fringing and parallel plate capacitances, and then we observed that in today's technology, really, when we have the situation that the height of the wire is much greater than the width of the wire, then we are really dominated by this fringing capacitance, as opposed to being dominated by this parallel plate capacitance long time ago. So that's important to remember. And then we also said, well, this was just for a single wire running on across dielectric material and our silicon substrate. But in reality, we have a lot of these levels of interconnect sitting on top of each other, and then we really need to start worrying about this interwire capacitance. So it's basically, where do these capacitances terminate? And so these components that were present before, fringing and parallel plate, are still the two most important components you need to remember. But a couple observations here. First of all, the total capacitance associated with a single wire is larger, because now you have more surrounding wires where you can terminate your electrical field lines. And second, as you go up higher in through the metal stacks, then you basically observe that your capacitance to ground is reduced, because you're getting farther away from dielectric, and you have also a lot of wires around that you terminate your electric fields to. And where is this all going with technology scaling? We observe that in today's technologies, when we are, for example, in this class at quarter micron technology, we can safely assume that interwire capacitance is dominant. So basically the capacitance to ground plate and capacitance to ground and parallel plate components are sort of diminishing. So all you need to worry about is this interwire capacitance that is dominant component in the total capacitance of a wire. And then another important component is a wire resistance. And then we also derive this simple model assuming a wire that is H tall, W wide, and L long. We have this equivalent resistance of a wire that is given by this rho over H, that is sheet resistance multiplied by L over W. Now, the reason why we wanted to actually keep the height of a wire the same is not because of a capacitance, but because of a resistance. Because if you assume that local resistances are scaling in the same way, basically that L and W scale in the same way that the wire length also tracks the scaling of technology and the scaling of wire width, then if you keep this height constant, then you have approximately constant resistance as you scale technology. If you start scaling down this H, then your resistance increases and you're in trouble. So you don't want to do that. People have already transitioned from aluminum interconnect, and now copper interconnect is widely adopted in semiconductor manufacturing, and there is basically not much more room to go. So you have to really start scaling technology in a way that you keep the wire height constant. And this is also interesting illustration that all you care for here is basically this sheet, this actually resistance per square. So a wire of this geometry over here would have identical resistance as significantly larger wire shown on the right hand side. So that's important to keep in mind. And then we went into discussion about how do we really capture the impact of RC on our circuits. And then we derived a couple electrical models that are suitable for hand analysis and understand the first order effects that are going on. So we first started with a simple lumped capacitance model where we say, well, let's assume that our gates are really slow and that the equivalent resistance of a wire is really not that big of a deal from the delay and performance standpoint. So we can then just simply approximate a wire as just one lumped capacitance that is driven with some equivalent resistance. But as we go toward higher frequencies, that no longer becomes true, because our gates are improving in performance and the wires are not following the same trend. So eventually we will hit the point where we have to start thinking about more accurate models for wires. And that's how we came to this distributed RC line type of model, where you have basically a wire, very long wire sliced into very small pieces of delta L long, and then you have to define parameters such as resistance per unit length and capacitance of a wire per unit length. And then we analyze this case in this using this diffusion equation framework, this expression over here, because basically when you inject a step response at the input of this wire, then it basically sort of diffuses through the material until it reaches the final destination, the output, as noted here. And that is described with this diffusion equation here. Now, what's really important that we came up last time, one result is particularly important, is that the delay of this wire is better than what you would predict by simply using this lumped RC model. And we said that it was about factor of 2 discrepancy. So if you're really lazy, you don't want to calculate really in great detail what's going on with this wire, you can just basically calculate a lumped RC divided by 2 approximately. It's not quite divided by 2, but delay of this RC lumped model is 0.69 RC. The delay of distributed RC line is 0.38 RC. And that's important to understand. Now, what this expression also tells us that this time constant of this distributed RC line is increasing quadratically with increasing the wire length. And that really becomes a problem for the global wires. So the idea is to keep wires as short as possible, to keep all the interconnect local, at least the interconnect that needs to provide really high frequency signals, and then you worry about the global communication in other ways. So this is a step response of a wire as a function of time and space. When you apply a step voltage at the input, this sort of illustrates that diffusion property and diffusion behavior when you get farther away from the source of the signal, from the input side. So you have length over 10, then length over 4, and so on. As you go farther away, you need to wait and wait until you develop a full swing signal at the receiving end. And we also observed that accurate analysis of RC network, such as the one given here, is very complicated. Even two-stage network with 2 poles is really getting tedious for analysis. I hope you haven't tried that at home, because it's really complicated. And then we introduced this simple delay model based on Mr. Elmore, who made this nice observation that basically your wire delay can be expressed simply by going through each of the nodes in the network and sort of observing what are the equivalent resistances and capacitances that are contributing to the overall time constant. So you can either go backwards and look at each node, see what's the equivalent capacitance, and then you sum up all the resistances that you see between the source and at the node and that node that you are observing, or you can go forward and basically see what are all the capacitances starting from certain node K in the network going all the way through the output that a resistance can see. So you can basically express this formula either as a sum of I going 1 through n over all the capacitances, and then you go upstream, calculate all the equivalent resistances, or you can basically sum up all the equivalent resistances and go downstream, calculate all the sum of all the capacitances to the output. This is basically how you come up with that expression of 0.38 RC. This is approximately 1/2, but when you do simulation, then you'll figure out that that's the number you're going to get. So let me now continue where we finished last time and do a couple of examples of this Elmore delay formula so you better understand what's going on, because that's a very important concept indeed. So as always, we analyze the propagation delay assuming step input. So that's really important to understand. It's also going to be useful for your midterm. So you have then a simple network like this: resistance R1, then we have capacitance C1, then we have another branch R2, and then we have C2, R3, and we have C3. And let's assume that our source is right here, and the destination is over here. So, and we're interested to calculate the propagation delay of this path. Now, what Elmore formula says is that time constant is equal to the sum over k, where k goes over all the nodes in the network, this node, that node, and so on, over all the n nodes, ck, and then you take this parameter rik, where rik is basically a fraction of IO path resistance that exists between any node and the input node k. So, for example, C1 sees equivalent shared resistance R1. Then we have C2. It sees shared resistance R1 plus R2. And then finally, C3 only sees shared resistance R1. It would see basically R1 plus R3, but you have over here R1 plus R2, only R1 is shared. So you have this formula over here. Now the question is, why do you have in your propagation delay analysis basically the impact of this C3? That was the question when we left off last time. And basically the explanation there is that the C3 is basically taking away useful charge that you would otherwise charge onto your on-path capacitances. And now again, you can argue this is still an approximation. You can still find extreme cases where, for example, you let R3 go to infinity or let R3 go to 0, and then these cases sort of degenerate into parallel combination of C1 and C2 in C3, or sort of cutting off the C3. And then this model basically works quite well when your resistances and capacitances are about the same order of magnitude, which is really the case in most practical circuits. Question?
Is it C3R3 or C3R1?
R1. Thank you very much. That's right. C3R1. R1 is the shared. Okay. So let's do another example over here. So we have R1, C1, R2, C2, and let's assume that this is our path, and we assume step input at this node over here, the source. So now the time constant is equal C1 times R1. C2 only shares R1. And C3 also shares only R1. So it's really important to understand this concept over here, this formula, and the shared resistance business. Okay. Another question.
So now suppose I want to discharge, and so my output is an opposite, means high to low transition at the output. So now if I just look at like time that it takes to discharge only C1, then it will be just R1 into C1.
The charge, oh, that's a really good question. So what happens if you want to discharge? Basically, you would also have charge leakage from these guys, because if you start discharging C1, there is still some energy accumulated on C2 and C3, which would basically be charging it back up. So you really have to consider them both, because that's the energy you have in your circuit. So this formula still holds. It's a good question. Another one. So the question is there any specific assumption about the relative values of mutual values of resistances and capacitances for this formula to hold? And that's a really good question. This is, as I said, just an approximation, but it is valid and pretty accurate in cases where you have the same order of magnitude, about factor of 10 difference between R's and C's in this particular network. If you have too large of a discrepancy, then this model becomes a little bit inaccurate. But luckily, the way you model your RC networks is basically by extraction of certain parameters for a given length that is approximately equal in all segments and so on. So you end up really with approximately the same values, or at least within an order of magnitude. Okay, so now let's analyze a case of a driver driving a RC network. So let's assume that we have a driving gate over here, and then we have our distributed RC network with total wire resistance RW and total wire capacitance CW, and then we have load over here. So let's try to calculate now the propagation delay of this particular structure when you apply, again, step input. So the equivalent model for that analysis would be this. So you have step input, then you have equivalent resistance of the source of the driver, and then you have this capacitance CL1, then you have RC due to wire, and we have load capacitance at the output. So let's label this node 1, node 2. So the propagation delay of this entire network would be equal to. So let's now apply Elmore delay because analysis, because that's what we're familiar with. It's really nice for this kind of complicated structures. So let's start with node 1. So we have CL1, and going upstream to the source. So it's basically now this is the path we are interested in. So this is our source, and this is the destination, and this is the path. So now we have CL1 times RS. For the CL2, we have the wire resistance and also resistance of the source. So we have RW plus RS. And this is all multiplied by 0.69. Now, for the capacitance of a wire, we have basically we see RS and we also see RW. Now, for the RS, we have this 0.69 CW times RS. And for the impact of wire resistance, because this was a distributed model, we have 0.38 CW times RW. Okay. So now, looking at this expression, what do you need to also understand besides just knowing how to write down the formula is basically always when you get some result, it's always good to sort of spend some time thinking what does it mean and when does it hold and so on. So when you look at this expression, you basically see various terms here, and now the question is, what happens in sort of extreme cases when my source resistance is much higher than my wire resistance, and when my source driver resistance is much smaller than the wire resistance, and that basically gives you insight into which model for a wire you really need to apply. Shall you go with a distributed model that's more complicated, or you just basically make use of the lumped model and your analysis is still accurate? So basically, when you have a scenario where your source resistance is, for example, in the kilo ohm range, which is realistic value from the analysis that we did a couple lectures back for the equivalent resistance over transistor, and let's assume that you have a very tiny wire, let's say 5 ohm wire, then you basically just say, no, just ignore wire, because that resistance is so significantly smaller than the source resistance, so you can just basically assume that your wire is a lumped capacitance. So you basically ignore RW in this case. Now, another case, when you make your transistor really large and your driver quite strong, then you have, for example, this case, when you have 50 ohms and then you have to drive a long wire for that purpose. Then you have, for example, 100 ohm resistance, then your wire is sort of dominant here, and then you need to include. Now the question is really, when do I consider the impact of wire, when do I not? And you really, what you need to do is basically compare the propagation delay of a gate and the propagation delay of a wire. And that's basically, when you understand the two, you can sort of derive some rules where you need to consider wire and when you don't need to consider wire. So now let's write down formula for the propagation delay of a gate. We know that that is equal to 0.69 R equivalent C load. And we also know that TP wire is equal 0.38 RC times L squared. That's the length of the wire. And this is unit length resistance and unit length capacitance. Now, it's really interesting to know where do these two become equal. And that happens if wire reaches some length that we call critical length. So we define this critical length of a wire as square root of TP gate divided by 0.38 RC. And what this formula tells you is if wire length is greater than this critical length, you really need to include a distributed RC model and take into account all of these wire parasitics. Another parameter that you really need to consider as well is also the rise time at the input. So that basically rise time of the input is determined by the driving strength of your gate and also what's loading the gate. So if rise time at the input is smaller than the RC delay of your wire, that means that really your wire becomes sort of dominant in the delay calculation. So that's another rule. So first rule is make sure that your length is higher than the critical length. And the second check is if the rise time at the input is sufficiently small compared to the propagation delay time constant of the wire, then you need to include also a distributed model and very accurate. If the opposite is true, basically that the rise and fall times at the input of the wire would be much higher, much larger than the propagation delay, that means that really your wire doesn't contribute much. It's basically just can be treated as a lumped model. So that these are the two rules that you need to sort of look at before deciding whether you go with the lumped RC model or distributed RC model. Okay? So now let's go back to slides. And this is type of RC models that you normally use in SPICE. Even simulation of the fully extracted RC, distributed RC model in SPICE can take a very long time because the way SPICE works is basically it inverts matrices. When you describe a system, you can basically describe it as a linear system with certain matrix of R's and C's and so on. So if you add more elements into the network, then you basically increase the complexity of your problem in a superlinear fashion, because now you no longer have linear increase with n, but you rather have n squared because you have matrix. That's how you organize. And then even in Spice, you make certain approximations for wire models. And then one way to do this is basically just say, well, let me assume that my wire resistance is really what's important to me over here, but my wire capacitance is sort of distributed equally both on the source and the destination side, and I can basically form this type of a model. So when I basically break up my wire, I can take segments that correspond to this model. And this basically captures many of these RC segments that we talked about with the slide of about the diffusion equation. When you divide up wire into really small segments, you maybe take a good number of segments and say, well, this is my sort of crude model for that schematic. Or you can take an alternative approach. You can say, well, let me assume that my capacitance sits in the middle, and then I have equally divided resistance from that point going back to the source and going forward through the network. And these two models are the most commonly used. This is called a pi model, and this is called a T model because of their geometric shape. And now you can do more precise models by basically putting together two pi models. You get pi 2 models. So now you basically have a finer granularity in your RC equivalent network. And you can go even further and do pi 3 and T3 model. Just to give you a flavor of the complexity involved, I did recently an example of a multiplier, 16-bit multiplier with latency for 4 pipeline stages, and a simulation of the entire multiplier, which has fair amount of gates without any parasitics, takes about half an hour. Now, if you include just basically a lumped models, then that takes maybe about 45 minutes to 1 hour. And then I just did one experiment for fun and say, well, let me throw at it just a fully distributed RC model, really precise, what you can do. And you know how long it took? 19 days. So don't try to do that. Basically, you can still get pretty accurate results with these models, and that's the reason why people really try to put simple models in, because they give you really accurate results, and the complexity of your problem doesn't blow up. Okay, this is the Elmore delay. We went through that, driving an RC line. And now these are the design rule of thumb. Critical length, the rise time has to be smaller than the RC, and that's where you consider a distributed model. Now, any questions about RC stuff? Everything clear? Okay, so now let's go into analysis of interconnect inductance. As we discussed last time, these RC models are really applicable for very low frequency of operation. Now, in today's designs, you have multi-gigahertz operation, and you have very fast on-chip signaling, where basically you have to take into account inductive effects. And what you have basically in this case, you have your wire, and let's assume that this is ground. Now you have a bunch of these distributed capacitances and so on, and then you have basically currents that are going through these capacitances and going back through this ground plate. So now what these inductances will cause you, basically, you will have ringing and overshoot, you will have reflections due to impedance mismatches, you will have inductive coupling, you will have also switching noise due to this L di over dt. So now the question is, how do we really analyze and extract equivalent inductance? We are familiar with RC. Now let's see what's the story for this case. And then there is a couple of approaches that you can take to estimate the equivalent inductance of a wire. So basically, one is, let's start with the definition. We know that when you have an inductance and you inject some current over a certain period of time, you have delta V. And that's certainly one way you can do it. But then this gets really complicated by the fact that when you have neighboring wires, you have all this inductive coupling and so on. So this is really sort of hard to estimate the inductance of a single isolated wire. So the second one is that you can basically just utilize the properties of environment of a wire and its geometry and some certain dielectric constants. So you basically have this expression. If you probably have seen this in your EM classes or physics classes, that you have a product of wire permittivity, dielectric permittivity and permeability is equal to the product of this capacitance per unit length and inductance per unit length. Now we have to take this with caution, because this is really applicable to the case where you have a wire that is shielded with dielectric, surrounding dielectric. But then you can pretty much then sort of take sort of average constants of dielectric, mu and epsilon, to make this analysis applicable, because it really gets complicated to analyze inductance when you don't have a scenario like this. For example, when you have coax or you have wire on top of ground plane and so on. And the third way you can sort of understand what's going on with the inductance is to observe that propagation of a signal through a medium is equal to 1 over square root of mu epsilon. And that is equal to C naught divided by mu r and epsilon r. Now, this mu r and epsilon r are the relative permittivity, and mu is relative permeability of dielectric. And this C naught is the wave propagation speed in vacuum. And that is equal to 30 centimeters per nanosecond. And this is a number you should remember, because that will really give you the idea of when do you need to consider these effects. Okay, so now let's go back to slides briefly. Thank you. So these are some of the common cross sections for a wire, and as I noted, that this expression CL is equal to epsilon mu is really valid for this case, and for all other cases that have a little bit more complicated unit length capacitance and inductance, we can sort of derive some equivalent C and L that will fit into this expression that relates nicely the speed of wave propagating through the dielectric and your material properties. So this is basically the environment in that we want to analyze and apply this theory to. So basically, you have defined wires on chip that are very short, and so you have various effects there. But let me kind of pop up one level up and see what's going on over here. So this shows a chip that is ready to be bonded. That's actually already like bonded over here into a package. And this is this standard scenario that you have basically this second level routing. If you assume that the first level routing is the on-chip routing, then you have the second level routing that you have to connect the pads from your chip using bonding wires over to these package interconnects. And then you have these package pins that are further connected into a printed circuit board, that you have your PCB routes. And this is really when you need to consider these transmission line effects, because in the PCB you have printed circuit boards of a size of maybe 30 centimeters, and you know already that the speed of your signals is really fast on the chip, that you would like to propagate those signals onto the PCB so you can test your chip. And basically this analysis that we are going to go through is really applicable for the PCBs, because you know that wave propagation speed is about 30 centimeters per nanosecond, and that's about the numbers that you're talking about in the PCB design. So obviously the goal here is to minimize the impact of this transmission line effect and sort of make the rise and fall times as slow as possible, so that you don't need to include all of these complicated models. Or when you look at it from the other way around, just make sure that your wires are sufficiently wide, or that, for example, in that case, the resistance is reduced, and you can sort of make your signals traveling on the PCB really fast, so you don't need to consider all these effects. But in reality, in most cases, you do. And this is basically just the overview of the big picture. Why is this important? So now, the difference between distributed RC model and this distributed LC model is in a way that signals propagate through the wire. So in the previous case of the RC model, we had basically just a diffusion equation, and the signal simply diffuses through the medium and gets settled to a final value at the output. Now, we have fundamentally a different concept over here that is called wave propagation. And again, you have seen this in your physics and EM classes. So basically what goes on here is that in the wave mode, the energy gets exchanged, transferred between the electrical and magnetic fields, or equivalently energy gets exchanged between the capacitive and inductive modes in your network. And the way we model this transmission line then is, if you go to the overhead, thanks, then we have a full model that includes resistance. Then we maybe also have some leakage over here, the current that go into ground, modeled by this conductance. Then we have inductance and capacitance per unit length. And then we continue with the same model. So now let's analyze what happens at certain distance x. If this is our x-axis, and let's say that at this point x, we analyze this node and see what happens at this with this voltage V. And let's assume that this is delta x over here, because that's really that one segment that you use to normally describe what's going on. You have resistance, conductance, inductance, and capacitance. So when you write down the equations for voltage and current, what you get is basically dV over dx is equal to negative R times I minus L times di over dt. And you have a minus sign because as you move farther away from x, your voltage is decreasing. So that makes sense. Also for the current, you have di over dx is equal to negative GV minus C, the current through this capacitance, dV over dt. Now, if you assume that conductance is equal to 0, which is a good assumption to make in most cases, ignoring this leakage, current leakage into the substrate, then you have the following expression. You have d squared V over dx squared is equal to RC times dV over dt plus LC times d squared V dt squared. And this is what's called the wave equation. Now you can notice also the diffusion equation in here if you just take a look at these two terms. But then you have this additional term over here due to LC. Now, in order to understand what's going on here and how does a signal propagate through the wire, we need to make some assumptions to be able to analyze this. And so now let's focus on the scenario where we are analyzing sort of this PCB level wires, when we assume that we have very wide wires that have a very low resistivity, that we use copper, that we can do all we can to reduce the impact of resistance. And then in that case, we can simply ignore this term and then sort of analyze what's really happening with this LC business over here. How does the signal propagate through? So basically in the diffusion scenario for RC, you have just basically signal going from source to destination and gradually developing voltage at the final destination point. And over here you will have basically signals that are swinging back and forth, reflecting from the source, destination, and so on until it's finally settled. So another important point over here is if we take this segment of delta x over here, so let's assume that this is point x, that the voltage here is V, and this is our delta x, and that we have some unit inductance L and unit capacitance C, and then we basically have a current that's looping back. So now let's assume that we start with a step response at the input, and that we observe this point x away from the input and assume that sufficient amount of time has elapsed such that we have voltage V over here and that we have no current to the right of this point x. So now in order for a signal to propagate through this delta x over here, so in order to establish a signal in this cube over here, what we need to do is basically we need to charge additional capacitance, put additional charge onto this capacitance equals C times dx over here. So what we have is equal to I is equal to dq over dt. That is equal C times dx over dt and times V. And now dx over dt is the propagation speed. So that's the wave propagation speed. So you have capacitance, propagation speed, and voltage. So now what's really interesting from this analysis here, if you take V divided by I, then you have, and you know that this is equal to 1 over square root of LC, that you get impedance, and that is also equal 1 over C times the speed over here. So it's from there. So what's really interesting is that a signal sees the remainder of the wire as a constant impedance. And this is really important and really interesting because you remember that with the RC model, we really cared about the length of the wire. Over here, we don't care. No matter what the length of the wire is, you always see the same impedance. And it is a really, really nice property, especially for design of our driving circuits and so on. But there is a caveat there. You basically need to be very careful about impedance matching, as we will see in a second. And this basically impedance over here, as you see from this expression, is a function of a dielectric medium and geometry of the wire and also isolator around the wire of the dielectric that we said were lumped into these LC parameters over here, because we had different wire geometries and we wanted to make LC is equal to epsilon times mu. And Z0 is not a function of the length or the frequency. Typical values are 10 to 200 ohms. And this is a constant real impedance. Okay. So now let's go switch back to slides. So that's basically the wave equation over here. And you know that the propagation speed is equal to the speed of light in vacuum divided by the square root of the product of these relative constants. And this is the wire can be seen as equivalent impedance that is real, and the values are slightly higher here than I just said. So it's about 100 ohm or so impedance. And these are some typical parameters for the propagation speed. For example, silicon dioxide has a propagation speed of about 1/2 of that in vacuum. So it's about 15 centimeters per nanosecond. And you can read more about this in this book by Bakoglu, or also there is another book, Digital System Engineering, by Professor Bill Daly from Stanford. He does pretty extensive analysis of wire and interconnect and transmission lines and so on, high-speed signaling. But for more discussion, you will also you can go to 241. This is just basically we'll do the introductory stuff over here. So now, very important to understand is that how does the wire transmission line terminate on the source and the destination. So we can basically analyze three extreme cases sort of to understand the trends and the behavior of transmission line. So a wire can be modeled as equivalent impedance Z0. So now at the destination end, we can have three different cases. We can try to sort of have matched termination when we terminate the output with the equivalent resistance of the same value, or we can do another two extreme cases. We can assume that the output is open circuit or that the output is shorted to ground. And in order to understand what's going on with the wave propagation in these three different cases, we need to define this reflection coefficient. And that is basically just simply the ratio of the reflected voltage and the incident voltage coming at this destination end. So we have incident wave shown here as basically these dots, this dotted region over here, and then we have some reflection going back to the source. And then using this formula, we basically plug in R at termination resistance over here. So basically in this case, when we have a perfectly matched case, we have R is equal to Z0, so we have reflection coefficient is equal to 0. So basically nothing gets reflected, which is really a nice case. Or we have basically in this case that R is infinite, so reflection coefficient becomes 1. Or in this case, when R is equal to 0, reflection coefficient is -1. So these are basically three extreme cases in terms of reflection parameters that we need to analyze. And now let's see what happens in over here. So to fully understand behavior of this transmission line, let's assume that we have certain source with impedance Zs. Then we have this wire. And we have a couple different cases. We have Z naught case A. We can have open circuit case B. And we can have short circuit case C. Now we have to define reflection coefficient at the destination. So that is basically load resistance minus Z naught, and Z naught is impedance of this wire, RL plus Z naught. And likewise, we also define reflection coefficient at the source, because we will really have to propagate back and forth and reflect our signal around to before we reach the final value. So we have Z, let's put RS minus Z naught, RS plus Z naught. And then for these three cases, we had reflection coefficient, in this case A, when we had Z naught is equal to 0. When we had infinite, it was 1. We had -1. So let's do one example over here where we assume that RS is equal to 5 times Z naught. That will give us reflection coefficient at the input of 5 times Z naught minus Z naught, 6 Z naught, 2/3. So now we need to make use of this equation, that at any point at the destination or the source, we have that our voltage is equal to the last value plus incident plus reflected wave. So now what really happens over here is that if you look at the source side over here, so you have this voltage is basically your voltage divider. So if you apply initial step, let's say of 5 volts over here, so what you would have is basically looking into the transmission line, you see only Z0, right? So you have a resistive divider here. You have Z naught divided by Z naught plus plugging in this number, 5 times Z naught times 5 volt. And this is equal to 0.83 volts. So what happens in this case, that due to this impedance relationship, you inject only one small fraction of your initial voltage step into the transmission line. So now let's see what happens when you go back and forth between these S and D nodes. So what happens over here is, so you basically have your T line, source and destination, and then this has reflection coefficient. So let's see, this is a function of time, and this is voltage. So now it takes a certain time of flight for a wave to propagate in one direction. So this is basically T flight. So that is equal to the speed of this wave divided by the length of this wire. So let's say that this is T flight. This is 2 times T flight, 3, 4, and so on. So if you assume that this is a 5-volt signal, then we have the following scenario. So we basically have first voltage step at the input, and this step resulted in 0.83 volts over here. So now it takes certain time for this signal to travel over to the destination end, and once it reaches the destination end, then the value at the destination will be equal to the previous value, which was 0, because we assumed that there was no signal at the destination, plus this incident waveform, 1 plus rho d. which is the reflection back. And if you assume that we had ZL is equal to infinity, then we have the load or destination is the same. So we had 1. So basically we will have that this signal will be doubled over here. So once it reaches the destination, so we have basically 1.66 volts over here. And then this signal now starts traveling back. And once it reaches the source side, so this is the Vs, and this is the Vd. So this still stays at the same level. And now once this guy reaches back to the source, then what's going to happen at the source, we will have Vs is the previous value of 0.83 plus this incident waveform that's coming back, 1 plus this guy, which is 2/3 reflection coefficient at the source side. And then you have basically your signal going like that, and so on. So if we go, so now you understand the principle, how does this work, right? So you have certain time of flight that you need to travel between source and destination, and also back from destination to source. And then you have to apply this formula that you have reflection at both destination and the source. And for that you define reflection coefficients based on termination resistance or termination impedance rather at the source, at the destination side, pardon. And you also have the driver source resistance at the source side. And then you basically apply this formula and roll over in time to figure out these waveforms. Question? That's a good question. Basically, what happens is that voltages are always. Do you have a negative sign when you're coming back? You don't when you consider voltages. When you consider currents, you do. Say it again. You have R. That should be minus there. Thanks. Because you have the way you define it, basically, if you read it in the book, you have basically that your V is equal to V incident times 1 plus reflection, and then you have the current is equal to I incident 1 minus this guy. Okay, so let's go back to slides to see what happened in these 3 cases. So this is all assuming that the load resistance is infinite, so that's basically open-ended termination. And here we plot 3 different cases of source resistance. Now we have a source resistance that's much larger than the line impedance. Then we have matched case, and we have very small source resistance. And this plots red is destination, and this dotted dark line is the source voltage. So what happens in this case that we just started analyzing is basically over time, due to these reflections, you will have to wait certain amount of time for your source and destination to fully establish at the final value. And this was because of impedance mismatch. So you have very long rise time determined by this time of flight back and forth. Now, in this case, you have perfectly matched scenario where you basically inject 1/2 of the waveform initially, then the other half comes back from the reflection, and you immediately establish the final value. And this is another extreme case where you basically have overshoot, and then you have to go back, and so on, and then you have some ringing until you establish the final value of 5 volts. So now clearly this case is the most effective. And this is what you would be doing if when you design your PCBs, to make sure that you understand the transmission line properties and try to match that with the driver that is coming to drive that transmission line. And this can be really analyzed in a nice format by using this lattice diagram that is shown here. So let me go back to slides and back to the overhead and then explain you how this is done. So basically what you need to do for this lattice diagram to figure out the values of source and destination voltage is plot this over time in a following way. So let's say this is our source and this is the destination. Over here you need to know your reflection coefficient, and for the particular case that we analyzed with Rs is equal to 5 times Z naught and RL is equal to infinity, we had that this one was 2/3 and this one was 1. And you label this as a time axis. So let this roll over in time. Let's start from 0. So initial value that we had over here is 0.83 volts. So that was basically purely determined by that voltage divider when we apply the step input. Now, this signal then travels, gets injected into the transmission line. So let's say this was a transmission line over here. And incident wave is equal to that value that is injected into the line. After time of flight, here, T flight, at the source end you have reflection. So what this reflection coefficient of 1 means that the reflected wave is equal to the incident wave. And then you have, again, 0.83 coming back. Now, the value at this node is, remember this formula, so basically you have either source or destination is equal to the V previous or last value plus incident plus reflected. So now this is your VINC, and let's use another color. This is your reflected wave over here. So now in this case you have your incident wave is basically the same as this one, 0.83, but since you have a reflection coefficient of 2/3, only 2/3 of that value will reflect back over here. So you have 2/3 times 0.83, that is equal to 0.56 volts. Now the value over here, it's the previous value, so that's 0.83 plus this incident waveform, which was the reflected waveform from the other end, is equal to another 0.83, and it's equal also plus this 0.56. That's equal to 2.22 volts. Okay, now you understand the methodology, and now you just basically roll this forward in time. So over here you have the previous value. This was 1.66 volts. Now this will become reflected over here, 0.56. So now you will have 1.66 plus 2 times 0.56, that's equal to 2.78. Now 2/3 of this guy get reflected back, so this is 2/3 times 0.56, that's 0.37. This is now previous value plus these two becomes 3.15. Then you have 0.37 get reflected back, you have 4.01, and so on. So now you understand the methodology, the way you analyze the transmission line. And in the discussions, TAs will help you with a couple more examples just to get this in your hands and understand what's going on.
Could you just explain what will happen like when my output is matched? Like my rho d at the output is 0, but the input is not matched. How will the voltage build up at that time?
That's okay. You want to use this lattice diagram or okay? Anything. So good. So basically, when your input is matched, what is going to happen is, oh, the output matched or input matched? Output matched. Okay, so let's assume the case output matched. So we have, was that? What happens with this analysis with the waveform? So we basically have to analyze RL is equal to Z naught. So we have RL minus Z naught so that is equal to, that's equal to 0 in this case. And then it really depends on your source resistance over here. So now, do you want to assume the same case that we analyzed, that RS is equal to 5 times Z naught? Okay. So what happens over here is basically you again start with 0.83 volts, and then you travel with that signal, 0.83 volts. Then when you reach this side, this basically becomes nothing gets reflected, right? Because you have reflection coefficient is equal to 0, right? What will happen over here is then that you have 0.83 plus, this is, the previous value is 0, incident wave is 0.83, reflected wave is 0, so you stay with 0.83. So you come back and you have nothing to reflect. So you have to stay at 0.83 volts. And then basically this will then again 0, 0. So basically you have one shot and your output becomes established with this divider.
Then I won't be able to reach my final value.
You won't be able to reach because you are limited by this source resistance in this case, because you inject only 1/6 of this V step.
In the voltage calculation, why do we include the reflected wave? I mean, you include the V last and the V incident, but why do we include V reflected?
Why do we include V reflected? Because that's basically the wave that gets added to your the total voltage at the output. When you have your incident wave, then depending really on what's your termination, you may have effect that that incident wave gets amplified if you have rho greater than 0, or it can get attenuated. Actually, that you reminded me now of a good point. There is a on the class website, if you click on resources, there is a really nice animated response to answer your question about propagation in transmission line. So you basically start up a web interface, and then you can specify your Z source, you can specify your Z termination, and you can basically just click start in time, and it will basically show you how these waves go back and forth, and it will simultaneously plot the time response at the destination end. So you may want to play with that, and hopefully that will become clear. But that's basically just the formula you use. You have that your total output is incident 1 plus the reflection coefficient. And so this was all analysis for the lossless transmission line, when we assumed that the resistive effects were negligible. And that is basically a fair assumption in most cases for the PCB level analysis. Now for the on-chip analysis for high frequency signaling, we have to include oftentimes resistive effects into account. And what we are going to end up with then is basically a lossy transmission line, where we, in addition, on top of this reflection and business, we have also attenuation along the way. So we basically have a combination of what we just analyzed in today's class. In previous class, we have also a diffusion. So intuitively, what happens in that case, and you will hear more about that in 241, this is not really a 141 topic, is that your step at point x is equal to step at point 0 times e to the minus r divided by 2 z naught times x. And so that is the lossy transmission line, and you need to include all of these effects. So now let's go back to slides and wrap this up quickly. We'll review this last time also. So here are some of the design rules of thumb. When do I need to include transmission line effects? When do I need to worry about it? So basically, similar story goes as for the RC type of analysis. Transmission line effects should be considered when the rise and fall time of the input signal is smaller than the time of flight of the transmission line. That means basically that the time of flight is really something that dominates your delay calculation. And this is a simple rule that the rise and fall times should be smaller than about 2.5 times the time of flight, in which case you need to consider transmission line. Or transmission line effects should be considered when the total resistance of the wire is limited in a way that when you keep increasing your clock frequency, then the wire stays the same, but your inductance kicks in. And then you have to sort of really consider the full transmission line model. And this happens when the total resistance is less than 5 times the characteristic impedance on the transmission line. And finally, transmission line is considered lossless, where the resistance is really small. And the rule of thumb there is that resistance has to be smaller than 1/2 of the characteristic impedance for transmission line to be considered lossless. So we'll review this briefly next time, and I'll see you this evening in review session.